Hi everyone, Mr. Neighbor here, and we're going to talk about section 13.2, simple machines. So there are 6 simple machines that we're going to talk about, and the first of those is the lever family. So levers can be defined as a rigid bar that pivots about one point, which we call the fulcrum, and that is used to move an object at a second point, the output force, by a force applied at a third point, the input force. And levers are classified into 3 different classes. And the classification is determined by the location of the fulcrum, the load, and the effort. Or you might want to think, instead of load, the output, and effort, the input. So I'll just write that right here. So in, out. All right, so first class lever, probably what you're most familiar with. It's kind of like a seesaw where you have the fulcrum, the input force over here, and the output force over here. Second class levers, the fulcrum is at the edge, and the input force is also at the edge. So I like to think about these as doors. And the third class lever is the input force very, very close to the fulcrum, the output force very far away. A lot of muscles deal with this, where the input force is near your elbow and you're lifting the output force, which might be your hand, the thing far away from the fulcrum, the elbow. So let's look at those in more detail. So the lever family. First class levers. The fulcrum is in the middle, somewhere in between the input and output force. It multiplies the effort force and changes the direction. Some examples would be a crowbar, scissors, pliers, or a seesaw. Second class levers. The load or resistance is now in the middle, in between the fulcrum and where you are applying the input force. It multiplies the effort force, but does not change the direction at all. Some examples would be a wheelbarrow, a door, which I mentioned before, a bottle opener, or a nutcracker. Third class levers. The effort is in the middle now, and the output force is on the far end. It multiplies the distance and speed. So you would have to apply more force, but it's going to travel a greater distance and it's going to move faster. So this might not move very fast, but further out on the edge, it will move fast. So that's the whole point of a third class lever. You have to apply a lot of input, but your output has a lot of speed to it and moves a great distance. Some examples might be tweezers, hammer, shovels, and muscles are in that category. All right, the mechanical advantage. We've been talking about that along with the mechanical efficiency. Now we're going to look at it in terms of levers. So normally mechanical advantage is calculated by your force out divided by force in. And that's true. However, to calculate with a lever, you're going to divide the length of the input force divided by the length of the output force. So this length right here, this length right here, that's visible. That would be the import or the input length, so L in. This would then be L out. This would be the import length. Input, I'm saying import. And this would be the output length. Notice how they overlap in this scenario. Over here, they will also overlap. So here's the input. And over here is the output. So different mechanical advantages. You're going to see some come out to be less than 1, and that means it's not a good lever because it requires a lot of work, but it serves a different purpose maybe. So just remember that the purpose might be why it has such a low mechanical advantage. So let's do some practice. All right, Alex pulls the handle of a claw hammer with a force of 15 newtons. If the hammer has a mechanical advantage of 5.2, how much force is exerted on the nail in the claw? So a claw hammer is your typical hammer that you would normally have, as I kind of have pictured here. There's the nail in red, hammer in green. If you apply a force to the hammer, you would be applying it this way. And that would be pulling a force on the nail this way. So the force has been redirected. That is a first class lever thing. So the mechanical advantage is 5.2. We have known mechanical advantage always to be the force out divided by force in. So if he's putting in a force of 15 newtons and getting out a 5.2 advantage, that means we're missing the force out. So times 15 by 5.2, and we will get the output force on the nail. Which is 78 newtons. A construction worker uses a board and log as a lever to lift a heavy rock. If the input arm is 3 meters long and the output arm is 0.75 meters long, what is the mechanical advantage of the lever? First, I would go ahead and draw a picture of the scenario just so you know what it looks like. All right, I have my picture. Looks like a first class lever. The input I am going to be applying right here. That length from here to the fulcrum is 3 meters. So 3. And we're going to divide that by the output length, which is right here, which will apply a force this way. That will be 0.75 meters. So the input length is now on top. The output length is on bottom. So when we divide that, we will get out 4. So 4 times as easy to do this work with that type of lever. Our next simple machine is the wheel and axle. It's essentially a lever that rotates a circle. So if you think about this as the fulcrum, this is our lever right here. However long or however big the diameter of the axle, that's like our input force. And the rotation of the wheel, that's the output force or work. So it's essentially a third class lever. So wheel and axle, just a big lever. The mechanical advantage for the wheel and axle can be calculated by the radius of the wheel divided by the radius of the axle. So the axle, that's the work that you're putting in. You're putting in the work to turn that thing. And then you're getting out the bigger the bigger wheel's rotation. So that's why the wheel is the output and the axle is the input force. Right. The gear attached to the rear axle of a bicycle acts as the wheel in a wheel and axle simple machine. The radius of the gear and the wheel are the input and output distances respectively. If the gear and wheel combination have a mechanical advantage of 6 and the wheel has a radius of 0.5, what is the radius of the gear necessary to produce this mechanical advantage? All right, so mechanical advantage for wheel and axle will be the radius of the wheel divided by the radius of the axle, or the gear in this case. We know the mechanical advantage is 6. We know the wheel's radius is 0.5 meters, so we need to find the radius of the gear. So I'm going to swap the 6 and the radius of the gear around to solve for R. And this will calculate out to be 0.083 repeating meters, or rounded to 0.08 meters, which makes sense for a gear to be smaller than the bicycle wheel. and this is the radius, remember.